working on some optimization problems. This problem about a farmer has to do with rectangular area. So area of rectangles, and we can see the picture over here. This is not simply a like x times y for the whole thing. It's not just length times width. However, we are going to use length times width. Usually when we talk about fencing, we're talking about area of a rectangle and the perimeter, right? Because a fence is the distance that's all the way around something. Now, this particular drawing and this example, we also have fencing here and here. So we're going to have to add up and identify all those little pieces, whether they're X's, whether they're Y's, whatever. We just had to figure out all of the lengths put together for that perimeter. Okay, so we've got 100 yards of fencing that's going to form two identical rectangular pens and a third pen that is twice as long as the other two pens. Okay, so we've got two identical rectangles, X by Y, and then a third rectangular pen, which is twice as wide as one of the little pens. Okay, so this would be Y and this would be Y, right? Because if they're rectangles, opposite sides are congruent. And then, of course, if this is Y and this is Y, this side is 2Y, which is just Y plus Y. Okay, it says that the pens all have the same width, which is X. So this is X, this is X, this is X, this is X, and this is X. That's a lot of X's. Okay. We want to know which value of Y produces the maximum total fenced area. So let's start by writing our sentence. When Y equals blank yards, the fence has a maximum area. That way you know what you are doing at the end. You know what you have to find, so you know if you've gone far enough. So sentence first, we're looking for Y. All right, our primary equation is the equation that we need to maximize or minimize. We are trying to maximize the area of a rectangle. We want the area of the whole thing, not just the area of this little guy. So our primary equation, I'm just going to put primary, is area equals length times width. Now, of course, we do not have the length or the width. Specifically, we have X's and Y's. So I'm going to rewrite this that instead of length, which is going to be this guy right here, that's going to be 2Y. And W, instead of width, we're going to have X plus X, which is 2X. X. All righty. Let's simplify that out. 2 times 2 is 4, so area equals 4XY. This is what we want to take the derivative of. The problem is that we have 3 different variables. What we really want is to have one variable type on the left and one variable type on the right. So that means that we need some kind of an equation that relates X and Y together so that we can make basically a system of equations. Okay, so for our system of equations, we want X and Y to be in another secondary equation. I try and write my secondary off to the side because we're going to use this primary a whole bunch. The secondary is going to get used at the beginning-ish and then again at the end. So this is all going to be primary work, and then this is all going to be secondary. Okay, our secondary information is going to include the fact that we have 100 yards of fencing. We talked about how that's the perimeter, so I'm going to put P equals, well, the perimeter is all of the fencing combined. Now, I know perimeter in general is like just around the outside, but it's also going to include these Y's and that X. All right, so how many X's do we have all together? 1, 2, 3, 4, 5. 5X plus 2, 3, 4, 5, 6 Y's. So P equals 5X plus 6Y. And we know in this case that the perimeter is 100 yards. Okay. The thing that we actually want to find is y. Since we don't care about x, let's try and get it so that we have x by itself so that we can substitute in things with y in here. So this will just have y's. So we have to get the second equation in terms of x so that we can substitute away the x. We only have y's left. That means we need to subtract 6y and divide by 5. So 100 minus 6y equals 5x. And as I divide by 5, I'm going to divide each term separately by that 5. It's going to make this 100 over 5 a little nicer to deal with. It's going to be a 20 minus 6 over 5y equals x. You could change that to, what's that, 1.2? If you felt like it. Okay, so this is our secondary equation. It's going to get plugged in here for x. So a gets substituted. A equals 4 times 20 minus 6/5 y times y. Would have been nicer probably to write the y there with the 4 for distributing purposes, but whatever. Let's distribute, because we would rather distribute now and use power rules instead of do like a product rule. 4y times 20 is 80y minus 4y times 6/5, so that'd be 24 over 5y squared. All right. We take a derivative now. So I'm going to write derivative out here. This is going to be dA dy. We are taking our derivative with respect to whatever this variable is. So this is going to be more like implicit differentiation from when we first learned it, when we just had x's and y's. We took the derivative with respect to x. Here we're taking the derivative with respect to y. So the y's are going to feel normal. They're not going to have like dy dy's. Okay, so 80y's derivative is 80 minus 2 times 24 is 48 fifths y to the first power, so that's just y. All right. dA dy. We want to find where we have a maximum. Maximum and minimum, those types of things happen where the derivative equals 0, right? Where we have a maximum, the slope is 0, the slope of the tangent line. So we plug in 0 equals 80 minus 48 fifths y. Move that fraction term over to the left, making it positive. 48 fifths y equals 80. And then multiply both sides by 5 over 48 to cancel out the left, and we get y equals, where'd that go, 8.3 repeating. Guys, we found y. That's what it asks for. So when y equals 8.3 repeating yards, the fence has a maximum area. Now, I'm going to keep going on this because most of the time the problem asks for you to also find x, like find the dimensions or which values of x and y. So I'm going to keep going even though we know that we can stop here because of the wording of this problem. Okay. If we also want to find x and we know the value of y, we can take this value of y, which is 8.3, and plug it right in there for y, getting x to equal just a number. So it's going to be 20 minus, and I'm going to do the fraction version of this, which was 25 over 3. So 6 fifths times 25 over 3 equals x. A little cross canceling, 6 and 3 cross cancel to get a 2, 5 and 25 cross cancel to get a 5. So this reduces to 20 minus 2 times 5 is 10 equals x, which means that 10 equals x if we really wanted to know that x is 10 yards. Now what you could do if you really felt like it is you could plug in the 10 for x back in here. You could plug in the 8.3 repeating or the 25/3 here for y, and then multiplying all of that together and adding in all that will get you 100. Our next example is not so much world-based as graph-based. I'm going to draw a little graph out for this. Our graph is going to be y equals t cubed plus 2. So let's draw a little x and y axis. And let's do red for this first one. Y equals t cubed plus 2. Oh, and it says t is greater than or equal to 0. So, gonna look like that, because it should be like a cubic function, but we're not looking at the left-hand side. And our second one is y equals t squared. So t squared is gonna look like this. T cubed obviously should increase faster than t squared does. I probably should have made that steeper, but I don't have any whiteout with me, so this is how it's going to be. Okay, we say that both objects begin at t equals 0. At what time is the distance between the objects a minimum? Okay, so we want to know at what value of t is the distance between the objects a minimum. So really what we have to do is subtract their y values, right? This y value minus this y value, because it's at the same time, that will be the distance between your objects, because S1 of t and S2 of t are the positions of them. So subtracting them, their positions, tells you how far apart they are. All right. We are trying to minimize the distance. That's what it says to do. If both objects begin at t equals 0, nobody gets a head start. At what time is the distance between the objects a minimum? All right, so our primary equation is the one that we are trying to minimize or maximize. In this case, we are trying to minimize the distance between S1 of t and S2 of t. I'll color those in. That one's red and this one was blue. Okay, find the distance between those. Well, we can do a little bit of substitution. We know that S1 of t is t cubed plus 2 minus, and we know that S2 of t is just t squared. And that's just a polynomial. Heck yeah. D equals t cubed minus t squared plus 2. In this case, we do not need a secondary equation, and here's why. Our goal is to get one variable on the left and one variable on the right. We do only have one variable type on the right-hand side of this equation, and it's t. The goal of the secondary equation is to rewrite a second variable over here as whatever we care about, which in this case is t. All right, so let's minimize this equation. We're going to take a derivative. There's no substituting. We're going to take a derivative, which will be d capital D dt equals 3t squared minus 2t plus 0. And since we're taking our derivative with respect to t, we do not need to use that chain rule bit, like in related rate stuff. All right, we set our derivative equal to 0 because we want the minimum, and that happens where a slope is 0. And this curve, whatever it is the distance between the two curves. Those would be all the y values of that. Okay, so 0 equals 3t squared minus 2t. Factor out a t. T times 3t minus 2. So that means t equals 0. And t equals, what, 2/3? Positive 2/3. We are told that t is greater than or equal to 0. Both of these t values fall into that domain, so we're good. At t equals 0 and at t equals 2/3, there are possible mins or maxes. These guys are critical numbers. Okay, so it's possible that we could have a min. It's possible that we could have a max, which hopefully that makes sense. We've got a squared function. Our original function was cubic. So the original function looks something like this. This is the function of d. So we should have a maximum and we should have a minimum. If we go back to algebra 2 stuff, since t cubed, that leading term is positive, it's going to be this shape, not this shape. It's definitely going to look like this, which means the first one has to be the max and the second one has to be the min. However, we're going to go ahead and use a sign chart to figure out which one was which officially. All right, I'm going to start my sign chart at 0, and it's going to go forever. Here's 0. This is a sign chart for dt. 0 and 2/3. And let's plug in like 1/3 and like 1. We're plugging this into our first derivative. All of these lines are the first derivative. I'm going to pick this one because then I just have to figure out the sign of each factor and multiply those signs together. So if we're plugging in 1/3 for t, that's positive. Over here, 3 times 1/3 is 1, and 1 minus 2 is -1. So it's a positive times a negative, which is negative. Now I'll plug in 1. 1 is positive. 3 times 1 is 3. Minus 2 is 1, which is also positive. So positive times positive is positive. Okay, that means that we had a negative slope and a positive slope. So this would be t equals 0, and this would be t equals 2/3. Max, min. D has a minimum at t equals 2/3. D has a minimum at t equals 2/3. Now you might be thinking, why did we not make one of these charts in the previous example? That's because I forgot. Let's fix that. I'm going to go back up here. I was so excited about finding x that I forgot to make a sign chart, huh? Okay, let's see. We're back to the maximum total fenced area. We want to make sure it's a maximum, not a minimum. So at x equals 8.3 repeating, we're going to, y equals 8.3 repeating. We're going to make a sign chart for dA, dy. Y cannot equal 0, right? You can't have a distance of 0. You can't have a pen that has 0 for a length. So 0 all the way to infinity, and this is going to be our 8.3 repeating. I'm definitely writing it as a decimal on the sign chart because then it's easier to tell what's in this interval and what's in this interval. We know that it equals 25/3, but like, what is that really? Okay, so I'm going to pick a number. How about 1, and then how about 10? We really want to show that this is positive and this is negative in those intervals. So first derivative here, if we plug in, I should have plugged in 5. I'm going to plug in 5 instead of 1, because 5 times 48/5 is 48, and 80 minus 48 is positive. Over here, let's plug in 10. If y is 10, 10 times 48/5 is going to be like 2 times 48, which is, what, 96? 80 minus 96 is a negative number. Boom. Okay, so that means that A was increasing and then decreasing because its slopes are positive and then negative. Positive slopes increasing, negative slopes decreasing. So yes, in fact, 8.3 repeating for y does give A maximum.